our second and last speaker for the day, because the third session that was earlier scheduled was moved to tomorrow. Samuel is going to talk to us about improving an earlier implementation of automatic differentiation using staging and fusion. Whenever you're ready, please go ahead.
Yes. Hello. Today I will be talking about staging automatic differentiation with fusion. And what I mean by that is that I'll be telling you how to write a fast but also correct compiler for automatic differentiation. Automatic differentiation, of course, being that set of techniques with which you can compute derivatives efficiently, avoiding the pitfalls of symbolic differentiation and numerical differentiation, and have this be both fast and as accurate as we want it to be. But first, I'd like to say something completely obvious, which is that a good algorithm is an algorithm that is fast and hopefully also correct. This is no less true for AD, but unfortunately, often faster and more sophisticated algorithms are also more difficult to prove about. And of course, for AD, we have a rich literature and a lot of work on how to write fast and efficient implementations, which sometimes come with impressive and complex proofs of correctness. But we also have some literature on how to write algorithms with simple proofs. But these tend to be a bit disjoint. Now, obviously, that means that for today, our goal is to write a fast algorithm with a simple correctness proof. On the topic of algorithms with simple correctness proofs, we already know how to make those. And in particular, we know how to make this one, reverse AD, which, like all AD variants, computes the value of an expression or the primal and the derivative of the expression or the tangent simultaneously. But if we use this to take the derivative of xyz at 1, 2, 3, it actually gives us back the derivative in a sort of backpropagator form. And to get the actual derivative out, I have to give it the 1 and 0 vector. But this gives me, obviously, the correct derivative. And because this algorithm is calculated, it becomes correct by construction. And by using this backpropagator form of the tangent, it's also asymptotically fast. However, the derivative is computed by recursively combining these backpropagators. And it turns out that combining these backpropagators in this form is actually a bit expensive, and this makes the algorithm relatively slow or have a large constant term. So the situation we're in is that we know how to make a fast and easy to prove correct algorithm, asymptotically fast, I should say, but it is relatively slow compared to other implementations. In contrast, I could have just given you this not very self-explanatory piece of code, which also computes the derivative of xyz, but here you'll just kind of have to take my word for it that it does. However, the good news is that this is exactly the content of our paper. And in fact, I won't give you this piece of code. I'll tell you how to compute or calculate, derive a compiler from reverse AD. And to do this, we'll first prove quote fusion. And this will give me from reverse AD a simple but not very good compiler. And then I'll demonstrate how we can apply the principle of fault fusion to gradually turn this compiler into a slightly better compiler. And along the way here, we'll discover how to integrate monetic sharing into this approach. And to finish this off, I'll demonstrate how you can actually very easily extend this calculation with even further optimizations. Now, before I can start calculating, I'll actually have to tell you what this mythical reverse AD algorithm is. And this algorithm, actually, before we can even start taking derivatives, we need expressions to take derivatives from. And in this case, I'll use the polynomials. Expressions, of course, exist to take derivatives of, or, well, to be evaluated, I should say. And in particular, we'll evaluate them into numbers. And in our case, these are just things with ones, zeros, addition, and multiplication. Okay. When I use this evaluation to evaluate an expression, x, y, z at 1, 2, 3, it again goes on and recursively combines the results of x, y, and z to give us the final result, 6. But if I wanted to take derivatives, I could also use eval. But this time, I'll use eval on dual numbers, which are just fancy pairs of numbers and their derivatives. And we can give these dual numbers, or we can treat them as numbers by reading the rules of differentiation as their operations. And because now dual numbers are numbers, I can also evaluate into dual numbers. And if we do this, you'll see that we recursively combine the derivatives of the subexpressions to get the derivative. And actually, you might note that this algorithm corresponds essentially directly to forward mode automatic differentiation. But we wanted reverse mode automatic differentiation, and the way we'll get there is by using fold fusion. And fold fusion says that if I have a homomorphism H, and being a homomorphism just means that it preserves some sort of structure, which in our case is like zeros, ones, addition, and multiplication. Then, if I evaluate and then apply H, this is actually just the same as evaluating with H. And what this means for us is that if I hit forward mode automatic differentiation sufficiently often with fold fusion, I can get reverse mode automatic differentiation. And this, in effect, tells us that it is correct by construction. Great. We'll extend this calculation by taking reverse AD and turning it into a compiler and having it produce code somehow. And the somehow here is by using stage programming. To do stage programming, we'll use template Haskell. And in template Haskell, we don't have one, but we have 2 stages of execution. We can write code for compile time and for runtime. And template Haskell adds the syntax for quoting expressions, with which I can put quotes around an expression and get the code of that expression. And conversely, a splice operator with which I can turn code back into runtime code. And what this allows us is this, that we can write programs that run at a compile time and produce code, and we can splice them back to produce programs at runtime. For example, we could consider the power function, and rather than defining it recursively, I can now just generate its function body, and we do this by defining the following make power function. But essentially, this is just the power function itself, but with some quotes and splices inserted in tactical places. And if we use this, for example, let's say we use it to compute the power of 4, x to the power of 4, we get the code of x to the power of 4, essentially. Now, The idea is that we can actually do something very similar to reverse AD. And I'll reiterate the approach of our paper, which is that by doing this, we stage reverse AD, and then we can optimize it. So the first thing we'll do is we'll stage the evaluator, and this will give us a not very good compiler. But then we can apply fault fusion and gradually make a bad compiler slightly better. But if we take the straightforward way, we'll actually run into an issue known in the AD literature as expression swell. But we can now easily sidestep this by using monadic sharing. Oh, that's small, okay. So let's get started. To stage the evaluator, I'll first actually note that the operations on numbers actually quite directly induce operations on code. In particular, I can just write the 0 of code as the code of 0, and if I want to multiply two pieces of code, I can just put a multiplication sign between them. And in effect, this turns code into a number, and numbers are things I can evaluate into. Oh, yeah, well, here's an example. For example, if I multiply 2 and 3, you get 2 and 3, okay. But now I can also evaluate into code. And for example, if I take the expression which essentially represents x times y, I also get back the code for x times y. And in other words, this actually means that eval has just become a compiler. Crucially, of course, it should be the case that compiling x times y actually gives the same result as interpreting x times y. And we proved this in our quote fusion theorem. We actually proved this in general for all kinds of faults, but I'll give the specialized form here. And essentially it says that quoting the evaluator is no different from evaluating into code. And this has two direct corollaries, which are that eval as a compiler is actually just the same as eval as the interpreter. And this directly applies to reverse AD, which is eval in disguise. And this will give us a compiler. Now this compiler is not very good because it quite literally dumps the input expression back into code. But we can improve on this by breaking up larger pieces of code into smaller, more manageable ones. And for that, we'll use the following homomorphism, which says that I can take a tuple, or the code of a tuple, and I can split it into a tuple of code. And by fusing this map into our compiler, I can now manipulate the primal and tangent separately again, and I can actually statically evaluate the multiplication here. If we do that, we get this. And this looks somewhat good, but it's actually not very good, because, as you can see, V1 and V0 actually appear in multiple places, which means that we're going to start computing the same thing many times over. So, well, we started from this multiplication and we ended up with something that looks like what should be the result. We would actually prefer if we could share these values between the primal and the tangent in a way something like this. Fortunately, this is something we can easily do by using a kind of continuation passing style code generation monad, in which we will be able to explicitly perform monadic sharing or let insertion. And The way we incorporate this into our calculation is, once again, by performing fault fusion. And this time we'll perform it with the return of the monad. Now, this gives us the next compiler, which does a little better, as you can see, and it has even simplified the multiplication without making a duplicative mess. But we actually can do better, because we can see that there's still these unreduced operations in the output of the compiler. However, I suppose that by now this approach is getting a bit boring, because we're going to actually repeat the same couple of steps very often now, which is simply that we'll note that the compiler produces some unreduced expressions in its output. Then we'll find the appropriate homomorphism to reduce these. When this seems to cause a mess, we'll apply monadic sharing once more. And then we can just fuse this homomorphism to get the next slightly better compiler. And I'll do this a couple of times over, but I'll spare you the details because the paper gives you those. But I'll summarize that we'll once take apart some functions, and this will simplify scalar vector multiplication. Then I'll take apart some other functions, which will simplify vector-vector addition. And then finally, we note that map is essentially traversable for code, which will simplify insertions. But I promised that this approach, extending this approach would be easy. So let me do that. And as an example, I use constant folding. So for example, if we have the code, or if we take the code of 2 and 3 and try to multiply it, how can we simplify the result? For this, I'll build a tiny language around code in which we can distinguish between dynamic and static values, and we also distinguish between static zeros, ones, and other constants. And for example, I can equip this with the operations, which just say that if I multiply two statically known numbers, this is just statically another constant. But if I multiply a number with something dynamic, I get back something dynamic. And we can show that this is correct, you might have guessed it, by using another homomorphism. So, in the end, this finally gives me the promised compiler, and I'll very creatively name it comp.ad. And as you might have expected, applying it to the expression xyz gives us this code. And as you can see, it no longer mentions any operations on vectors, maps, and such. These have all been statically reduced. But this time around, you no longer need to take my word for it, that it computes the right thing. We actually know that it does, because we know that it comes from this compiler, which we've shown correct by construction. Now we actually went on and figured out how much faster this makes everything. And for that we wrote some benchmarks. And we compared our compiler against JAX, a Python library for AD, and AD, a Haskell package for AD. And I'll note that we'll use double precision. We do allow vectorization, but to level the playing field a bit, we run everything on a single core. And furthermore, I'll note that the omitted data points actually represent crashes, which usually are out-of-memory ones. So while this does make the benchmark a little bit less realistic per se, it does give a good indication of how much faster we've made our compiler. For the first benchmark, we tested a linear least squares column, and as you can see, we have a good start and we perform quite similar to JAX. But JAX tends to still be a bit faster. I think the behavior on the right is actually a bug in JAX. I didn't look too deep into that, but unfortunately, before we get there, we also crash. We also benchmarked the logsum x function, and as you can see here, while we beat AD by a factor of over 50, we do get beaten by JAX quite significantly, and for a good reason, because as you can see, this problem is quite amenable to factorization, and JAX can make use of this to get a decent speed boost, while we do not, obviously. Yes, and this will come back in the future work. And finally, we benchmarked the naive definition of matrix determinants. And as you can see here, we actually significantly beat JAX and AD. So to summarize, we once beat JAX, we once almost tie it, and once we get significantly beaten by JAX. But to conclude, I have shown you how we can calculate a compiler for AD, and this reduces the performance gap with more popular AD libraries. But by virtue of its construction, is automatically correct. And furthermore, it is also very easy to extend this approach with more features or with further optimizations. And before I wrap up, I'd like to mention some future work, which is, of course, that we could still improve the compile time behavior. And one way we could do this, for example, is rather than compiling Haskell code, we might consider compiling to different languages. And the other obvious one is, of course, is looking into how we could extend our calculation with factorization. And if we're lucky, then maybe we can get closer in performance to JAX. And finally, I'd like to summarize some of the details I glossed over in this talk, but are very present in the paper, which are all of the preservation maps, of course, the entire calculation. And in the artifact, you'll also find a mechanized proof of quote fusion, along with, of course, the implementation, which includes all of the calculation and the benchmarks. That's all. Thank you very much.
Thank you. I have time for questions now.
I found the commutative diagrams in your slides quite helpful to understand what is going on. And I'm saddened to find that they are not in the paper. Do you have a version of your paper with those commutative diagrams?
Not yet.
How do you handle recursion?
We don't. So actually we work on a very simple language of just these expressions.
Yeah, but you also said it was easy to extend your language.
Yes.
I mean, if you come from the financial world, you might run something that takes half an hour to run and it's full of loops. So
yes. So of course we could extend. So first of all, this language doesn't actually allow you to share values yet. It is just polynomials. So first, we'd have to extend this calculation with let binding in the source language, which is actually something that is discussed in this paper in the top right. So first of all, we'd have to extend our calculation with that. And from then on, I think it shouldn't be that challenging to implement like loops and other control flow.
How would you store all the intermediate values? I mean, you can't unroll the recursion because you don't even know how big it is. Well, we can talk.
We can talk about this.
Any other questions? Okay, I have a question. You said the missing data points were crashes, essentially, out of memory, likely.
Yes.
Can you say a bit more on that? Did you look at memory consumption, both in your as well as the JAX crashes?
So I believe in this one, we run out of memory during compilation. When we produce some template Haskell, and when we actually go and compile that produces something intermediate which is too big. Which is why I mentioned that translating this to a more primitive language might save us. Because hopefully, like a compiler for LLVM, or maybe if we convert to assembly directly, would use a lot less memory. And for JAX, I'm not too well versed in JAX, but here very clearly in the just-in-time compiler for JAX, at least for a CPU, because in JAX you don't have very good support for recursion, so we define the determinant by writing this big loop over all permutations of the matrix elements, right? This just somehow blows up before we do.
If no other questions, then I have another one. You take a sequence of steps in improving your compiler, and
yes.
you argue, and I can kind of follow that there are improvements, but have you actually measured them midway through to check that each of them is an improvement?
Yes, this is in the paper, but I unfortunately didn't include that in the slides. We actually see that the very first step, in which we turn eval into a compiler, so we essentially dump the expression to code, this somehow produces something slower, but from there on, each of the steps improves everything by a small factor. And then at the end, of course, when we get rid of the insertions into maps, all of a sudden we go from logarithmic n log n time, we all of a sudden jump down to linear time.
All right, let's thank the speaker again.